Okay, I'm going to talk about evolved structures, how NASA is using generative design and digital manufacturing to make lightweight spacecraft parts really quickly. Things like these organic shapes you see there on the left and right. I'm Ryan McClelland. I'm a research engineer at NASA Goddard. And through this work, since it's kind of like caught into the zeitgeist of ChatGPT, it's gotten some media attention, and I've learned a couple of kind of funny things about journalism. One is they're going to come up with much better titles for your work than you could come up with, because they're in the interest of getting clicks. They like to use the word alien. Language smangwage, I kind of like that one. It's a little bit of an overstatement that we're not yet using it to build spaceships, but we're thinking about it. And a word of warning: if you work for a space agency and you say the word alien, it's probably going to get quoted. So you got to be really careful with that one. So the context of this work: this was developed with internal research funding at NASA Goddard, and the goal is to create and infuse a broadly applicable process to rapidly develop lightweight spacecraft structures. So it's really taking all the great work that the people in this industry have done and applying it and getting it in space quickly. And the method that we've done is to build and test parts for a lot of real NASA applications. I'm up to like 36 applications at this point, which really gives you a good idea of what the tools are and aren't capable of. And status, typical metallic structures that we build at Goddard or at NASA, and NASA's building like thousands of bespoke structures at any point. Small stuff can now be automated, and humans should probably largely stop doing it. We can go from, if it's a fairly simple part with just a couple interfaces, from knowing what the requirements are to having a part into ready for fabrication in just a couple days. And we've demonstrated this by testing on applications, and it's being applied to NASA missions that are going to go all over the solar system. The goals of this presentation: I want to share lessons learned about the practical implementation of generative design and digital manufacturing, and reduce the development time and cost by 10x. And for us, it really is having something that takes a month and having it take a couple days. That's the goal. And engage this community, because I don't think I've ever given this talk to a group that is more capable of giving great feedback, telling me what tools are coming, so that they can be really implemented into NASA missions. So the inspiration from this work, over the pandemic, I didn't have as much to do as I do now, which looking back was kind of nice. But I watched a lot of science fiction and things like The Expanse, which is great, by the way, if you haven't seen it. And I got looking at that, but I know how the sausage is made, right? Like, I know that the space station has 7 people in it and costs $100 billion. So that doesn't scale to the kind of structures that you see in science fiction. And that kind of bothers me, because I'd like to see that future where there's lots and lots of people living in space. So it got me thinking about how AI can be used to help do my work. I'm a structural engineer. I've worked on a bunch of stuff like Hubble and space station, and I just know that it's really slow and expensive. So this quote from the Google CEO, which is now actually kind of stale and probably getting kind of old, but that AI is one of the most important things humanity is working on, more profound than, I don't know, electricity or fire. So yeah, it got me thinking about how I can use that in my field. And then I found the work that you all have done in generative design. So this is the old DALL-E armchair in the shape of an avocado. This generative design, the AI gives you multiple design outputs based on your input constraints, and it collaborates with a human. So what really impressed me about this when I first saw it is man, it's using the pillow or the seat as a pillow is kind of has an aspect of creativity. So I got excited about it, and then now everybody knows about this. So this is a bit old, but the applications, visual art, text, of course, has just exploded with ChatGPT, music, architecture, and I'm going to talk about structural design. And in particular, I'm going to talk about taking it up a notch. So what if you want something more specific, like an astronaut in an avocado chair on the surface of the moon? Well, then you've got to do a little bit of better job of telling the AI what you want, right? So these are some attempts at that. You can probably, if you're familiar with this, you can probably see the difference between Midjourney and DALL-E in there. But I'm going to talk about how do you do this kind of like sophisticated prompt engineer. So here's my much more complicated prompt. Astronaut seated in an armchair in the shape of an avocado on the surface of the moon during the Apollo moon landings by Salvador Dali, blue Earth rise in the background. So that's the lower right or lower left image with the Earth. So it took some work to get that. So I'm going to talk about how you sort of prompt engineer to get lightweight parts for your spacecraft. And this is just a kind of a modern framing of it because everybody's thinking about prompt engineering these days. So the first step in this process is to digitally encode the requirements for the structure into a piece of software. And this is kind of an important step. So we have a very detailed written guide about how you do that. So if you have a quarter 20 through hole, there's a very specific prompt, CAD prompt that you put into that. So this is Fusion 360 being used for this purpose. So this is an example of what you might call a prompt. So the green parts are the things you need to keep. The red parts are the areas you need to avoid. I'll get more into that. And then you use generative design software to evolve the optimal designs that meet the requirements. And in this case, this is Fusion 360. And for some reason, this Mac is way faster than the PC. So I've never seen this GIF go that fast. That's kind of awesome, though. So it takes maybe an hour to make that, let's call it a prompt. It takes about an hour to evolve the designs, and then it maybe takes between a day and 3 weeks to make the parts. And then you test them, and they do just what you think. So really accelerating things. So I'm just going to get into this Excite tip tilt bracket a little bit, just so you see how this works. So it's a mission that's going to analyze exoplanet atmospheres from a balloon-borne platform. Very exciting. Launches from Antarctica. And really all you got to do is you just got to mount this. I'm red-green colorblind. It can actually take time, especially if it has strict requirements. So you have interfaces. You have a bolt pattern to the tip tilt stage. You have a bolt pattern to the telescope, and you have to avoid interfering with anything, of course. And then you have a bunch of gravity loads. So we often have G loads because we launch things. So we really need mass element representations. And then it has to be very stiff. There's a cryo cooler on this, and it's vibrating. So you have to avoid that cryo coupling it with that mode. And balloons can't lift that much, so it needs to be light. So how would a human approach this problem? So we did this, myself and a senior designer. The designer was doing the CAD. I was doing the FEA. And it did the kind of thing that you expect, right? You sketch in planes and you extrude, and then maybe you put in some ribs, right? That's what people do because everything is 2D, and it's just not nearly light enough. And then, well, it's not nearly light enough, so they put a bunch of pockets in it. Well, then it's not nearly stiff enough, and well, we're going to try to stiffen it up, but it's too heavy. It's not stiff enough. It's hard to manufacture. And then finally, he came up with this really wacky thing on the right that does barely meet the requirements, but is very hard to manufacture. So this is 2 days. We did 4 iterations, and that's pretty good for FEA and CAD. And if we had another couple weeks, I bet we could figure it out. But I want to contrast that with how we use generative design to solve the same problem. So the green are where the bolts go, and then the red is where the bolts have to come in. And they're very specific for the washer type used and the tool that's going to make this. And then there's also your load cases, of course, go in here, your manufacturing methods, et cetera. So then in about an hour, you get these outputs. And 2 of these we actually fabricated. One is CNC, one is additive. So in Fusion, you can have them do them all at the same time. And let's look at how they perform versus the human. So in 1 hour, it does 31 iterations, doing the CNC, A, and AM ones simultaneously. It's lighter. It's much stiffer, which is great for our applications. And one of the kind of surprising things is, maybe it shouldn't be, they're much stronger. So the peak stress is much lower, and they're easier to fabricate. The CNC one was made in just 3 days for $1,000. I don't have it with me, but I do have a bunch of little samples that Ren Scott made for me that I can give out. And there's also one of these brackets is over in the end top, took the same design problem and did their take on it. So that's actually this same design problem. So then we throw them on a shaker, and we make sure they do what they do. And it's FEA, it works, so they're pretty much perform exactly like you'd expect. So that's a very simple example with just two interfaces. And the story of this is that we're getting more and more complicated and pushing the tools beyond what Autodesk ever thought would be done with them, and making really complex things like these optical benches that have 7, 8 interfaces. There's a Venus lander here, and you can see that these are starting to get really, really complex and having a lot of interfaces. And the more interfaces you have, the longer it takes you because you have more requirements, but then sometimes the more savings you can get in terms of time. So yeah, it's very exciting to see these things are potentially going to be going sort of all over. So the alien spaceships will be our spaceships. That's my dream. So yeah, I really like this quote from Stephen Johnson. The trick to having good ideas is not to sit around in glorious isolation and think big thoughts. It's to put more parts on the table. So I've really focused on spending all my money. So how is this, to y'all, this is probably not that surprising, but to a general audience, they're like, wow, how can you get 10 times faster while also getting lighter, stiffer, stronger? And it's because, the advances of information technology that we haven't really fully harnessed, that we're just now starting to harness. So, our main tools are ProEngineer or Creo, which was from the 80s, and Nastran, which is, from the 60s. And, we've had 10,000 times computing power increase. And, what have we done with that? We've just put more nodes, and, our bolts now have the threads modeled. So, which is itself on top of FEA and on top of design for manufacturing. So, it's a paradigm shift in what the engineer does, and that's why, culturally it's been very hard to implement, because it's really, you do a different thing. So normally, there's some requirements and goals, and they may be pretty loose, and a CAD engineer or CAD designer comes up with, some thing in flat planes like that, and then throws it over the fence to find an analyst who's in a different group, and then they may take weeks to get results back. They might change some thicknesses, but they probably don't give a lot of feedback, a lot of introverts in this chain. And then there are, you make a drawing and then you throw over the fence to the manufacturer, and the manufacturer will just, look at it, curse the engineer for not knowing what he's doing, and give you like a really long lead time and high price instead of giving you feedback on how to make it cheaper. And this whole loop takes months and years, especially for complex things, to go between those people who go on vacation and have training, and it just is really slow. So generative design just collapses that whole thing, where you put in the requirements and goals, and then the software tool generates the CAD model, does a finite element simulation, does a fabrication simulation, and then you can just go make it. So it really is. We demonstrated being able to start with requirements and having a part in our hand in less than 2 weeks, and have that part, just be much better than a human designed part. So again, you can see how fast the process is. So I think I have plenty of time. So, I'm going to go a little bit into how this works. So, this box is kind of transparent to the user if the software is user-friendly. But what's really going on is you are, inputting the requirements, all these various requirements, and then, a lot of you already know this. It creates a voxel mesh of the space, and then the topology optimization is really the key to it. I'm finding I'm getting a lot better results with level set than with SIMP if you're, in the industry. And then, a key part of this is showing the outputs in a way that you can sort through them easily. So there's some good tools for this in the tool that we use, which is Fusion 360, and then it reconstructs it. So that reconstruction from that voxel to the a CAD model is hard, and when it's done well, it can be really enabling. So here's an example of to me and to the end user, you start with the inputs, and then you get something you can make. That's ideal. I think even further down the road and more ideal, you start with the inputs and then you get the fabrication G code at the end, but we're not there yet. So the other part of this is digital manufacturing, bits to atoms. So that's goes with the theme here. So on the left is a render that's done in Onshape, and on the right is the real picture, and they're pretty close. So digital manufacturing takes you from the virtual world to the real world, and just really broadly, you're making parts from CAD files without a lot of human intervention, and you all know most of this already. The software makes the G code, and the more advanced software, sort of the less the human needs to do it. So yeah, you see a CNC machine on the upper right, and then the lower right you see additive. A lot of people confuse digital manufacturing with additive, and I'm always trying to dispel that. I mean, this crowd knows, but there's a lot of other ways to make things, and I'll get into that. So there's a lot of automated CNC tools coming out now, where the CAM creates things very quickly, the computer-aided manufacturing software, and the robot just runs the G code. And one kind of exciting thing that I like is Proto Labs. We use a lot. It's like 500 Haas CNC machines and no machinists. It's just they just load in the blocks. So that's if you can get something to fit in their package size, it's pretty quick. And then additive, of course, the slicer generates the G code, and then the robot prints it, and then there's post-processing. So I'm going to sort of be a little bit real. What's the real state of CNC versus AM today? So a lot of these organic structures, like that, someone called it a tangle of metal in the middle there, that optical bench, that was CNC machined from a single block of aluminum, and it was done, very quickly and cheaply, in the scheme of things. And the whole thing is like within plus or minus 0.003. So that was a win over printing it. And there's, one of the really surprising things that came out is that there's an inherent stiffness. It's a compliance minimization algorithm, right? So there's an inherent stiffness in the parts that makes them easy to machine, much more so than the manufacturers were expecting. So that's one of those things you only learn by doing it. So with additive, you get more design freedom. So maybe I've seen you get like maybe a 20% bump in stiffness, and then some large monolithic parts can be cheaper to make, like big chunks of titanium. But for aerospace right now, there are a bunch of cost and schedule disadvantages. There's a limited choice of AM vendors. For a large titanium part, I had to go to Belgium, which had all kinds of issues with it. You all know about the material properties being process dependent, a lot of post-machining, the surface finish is rough, manual support removal. Heat treatment is usually required, and a surprising number of the manufacturers do not have an oven the same size as their printer. And NASA standard 6030 adds a lot of cost with where it is right now. And what was surprising to me is I get quotes back and well, this might fail a couple times when we print it. I'm like, oh. But for the future, it's really promising, and that's what a lot of people here are working on. As the technologies, the marketplace, and the standards are all rapidly maturing, and you're going to enable things like hollow structures. Though we did a lot of work with comparing in real applications hollow to solid structures, and we're actually finding that like having something truly hollow maybe isn't that big of an advantage. So maybe follow up with me, and I can send you my my intern wrote his thesis about it. But what I'm really excited about is large monolithic structures that are enabled by something like WAM technology, where you can take like a spacecraft like this. That is so expensive. There's so much manual labor and so many different parts that goes into making it's just a structure. So if you could generatively design one of those and then just print the whole thing in a month, that would be radically enabling. So that's sort of what I'm hoping to go toward in the future. So I don't know, how much time do I have? 3 minutes. Okay. So the summary you can just read. I already said all that. But the future, we want to make all structures 10 times faster and cheaper. Trusses, flexures, optics are things we're looking at next. And this is something that's really exciting that everyone's excited about ChatGPT. So one of my interns came up with a way to, instead of having to make the CAD that is the prompt, you just have a text prompt where you're like, I have a pattern of 1/4-20 bolts, and and it just based on the requirements, just builds the CAD model using like APIs. So I think that's going to be a really exciting, like plugging large language models into software so that you don't need to do a lot of the manual work. And then the other kind of fun thing is, this, and I hope if there's anyone who's working on this, I'd like to know this sort of trussification. So we used, Fusion to come up with this sort of, where's the load path going for this telescope application, and then we skeletonized it manually, actually, but it'd be nice to have that be more automatic. And then we turned that into tubes and nodes. And then the nodes themselves were actually designed using Fusion automated modeling. So that sort of we're trying to, the past missions that have had these truss structures, it's taken like a decade to design it, like literally a decade to design it. So maybe we can get that down to a couple months. So one of the things that is really interesting is that a lot of the challenges aren't technical, they're cultural. So everyone's building great tools, but how do you get people to use those tools? And especially get thousands of people, like NASA has like 80,000 people, to use those tools. And that is actually a lot of my work, is just trying to close the skills gap, because you do need to be inertia. And I've learned so much about how you get people to buy in that I'm happy to share with people. Yeah, and one fun anecdote I'll leave you with is it's really interesting with these, when you come up with a design and it's wrong, you just see it. We live our whole lives, we see bones, we see animals, we climb trees, and when you're climbing a tree and that branch it just doesn't look right, you're not gonna pull yourself up on it. And that's one of the fun things about this, is that human intuition is still needed. Okay, thank you.